Okay, now for what we have in the case of finding out what we have for eigenvalues and eigenvectors. And by theorem 7.2, okay, for eigenvalues and eigenvectors of a matrix, if we let A be an n by n matrix, okay, first of all, an eigenvalue of A is going to be a scalar lambda such that the determinant of the difference between lambda times the identity matrix I minus A is equal to 0. Second, the eigenvectors of A corresponding to lambda are the non-zero solutions of what we have such that lambda I minus A quantity times the eigenvector x is equal to 0. And the equation, the determinant of lambda I minus A quantity is equal to 0, that is going to be the characteristic equation of A. Moreover, when expanded to polynomial form, the polynomial where we have the determinant of lambda I minus A, again, you have is equal to lambda to the n all the way out to the constant c naught, and everything else in between you have with linear combinations that we have regarding the coefficient c sub n and variations thereof times lambda sub raised to the n minus whatever quantity. And okay, so for what we have in the case of the determinant of lambda times I minus A, that is going to be the characteristic polynomial of A. So the eigenvalues of an n by n matrix A will correspond to the roots of the characteristic polynomial of A. And just a sample of finding eigenvalues and eigenvectors. And let's say that A is going to consist of 2 and negative 12 at the top, 1 and negative 5 on the bottom. So A we have as a 2 by 2 array. And we have for looking at the determinant of lambda I minus A. Okay, so in the setup, we're looking at lambda minus 2, 12, negative 1, lambda plus 5, and looking at the determinant. Okay, so we come out to lambda squared plus 3 lambda minus 10 plus 12, which would be lambda squared plus 3 lambda plus 2, and in factored form, so that is going to be the quantity of lambda plus 1 times that of lambda plus 2. So the characteristic equation is going to be where the product of lambda plus 1 and lambda plus 2 is equal to 0, and this will give us the eigenvalues where we have from lambda plus 1, where we'll have lambda sub 1 is equal to negative 1 and lambda sub 2 is equal to negative 2. And to find the corresponding eigenvectors, okay, we can solve again the homogeneous linear system represented by lambda times I minus A multiplied by the eigenvector x is equal to 0 twice. Okay, first for the eigenvalue at negative 1 and then for the eigenvalue at negative 2. And for lambda equal to negative 1, we're going to have for the coefficient matrix, okay, that is going to be negative 1 minus 2, which is negative 3, 12. And then we have negative 1, and negative 1 plus 5 comes out to 4. And this will reduce to 1, negative 4, 0, and 0. And that will show that x sub 1 minus 4x sub 2 is equal to 0. And letting x sub 2 be equal to t, you conclude that every eigenvector of lambda sub 1 is of the form where we have the eigenvector is going to be the ratio, or in this case, you have 4t to t. And branching out, factoring out t, we have t times 4, 1. So the basis for this eigenvector is going to be 4 and 1. And for the second eigenvector, where we have set to negative 2, we will have for lambda I minus A, we come out to 1, negative 3, 0, and 0. And for what we have in the follow through, okay, we're going to have that x sub 1 is equal to 3x sub t. And letting x sub 2 be equal to t, we can conclude that every eigenvector of lambda sub 2 is of the form where we have x, the eigenvector, is equal to 3t and t, and factoring out t, where t does not equal to 0, we have times the basis for the eigenvector, which we have at 3 and 1. Okay, just sort of running a litmus test in terms of whether we have the given vectors to be eigenvectors that will correspond to the given coefficient matrix A. And let's say that for this item, if I have a coefficient matrix A to be -3, 10, 5, and 2, and I'm testing out 4 and 4, okay, so just looking at A times 4 and 4, okay, once you follow through and arrive at the product, okay, so we have 28 and 28, and that can be reduced in terms of 4, 4. In fact, we're going to have the eigenvalue at 7, while we have the eigenvector at 4 and 4. And since we have a perfect match, okay, the answer to this is going to be yes. And if I test out -8 and 4 to see if that is going to be an eigenvector, so just multiplying, okay, A and x of 2, okay, where x of 2 we have at -8 and 4, and following through we have 64 and -32, and I can reduce this in terms of -8 and 4, whereupon that eigenvalue is going to be at -8, and we have -8, 4 as the eigenvector, so that is going to be yes. Now, if I attempt -4 and 8, okay, now using that where I have A times -4, 8, we're going to have for that combination, we have 92 and -4, and that cannot be reduced in terms of the vector -4 and 8. So 92 and -4, that will not be a direct multiple or scalar multiple of -4, 8. So -4, 8 is not an eigenvector. And for what we have for 5, -3, if I multiply A and 5, -3, and just take the combinations, we'll come out to -45 and 19, and -45 and 19, especially since 19 is a prime number, we have this set of elements to be irreducible to 5, -3, so 5, -3 is not an eigenvector. Now, for what we have in testing out, let's say 1, 1, 0, first of all, if we have given the coefficient matrix A is equal to 1, 0, 5, 0, -2, 4, 1, -2, 9, and just looking at taking the product of A and 1, 1, 0, okay, this will come out to 1, -2, 1, and that is not reducible to terms in 1, 1, 0, so 1, 1, 0 is not an eigenvector. And for what we have for -5, 2, 1, okay, if I multiply out, now this combination is going to go to 0, 0, and 0, and we can say that treating 0 as an eigenvalue, well, we're going to have 0 times -5, 2, 1, which will come out to 0, 0, and 0, and since we can have a match, we can confidently say that -5, 2, and 1 is going to be an eigenvector. And for x is equal to the 0 vector, well, the eigenvector is supposed to be non-zero, so that is going to right away be no. And for what we have with D, okay, so we have x equal to 2 square root of 6 minus 3, -2 square root of 6 plus 6, and 3. And running it through the process. And what's going to happen here? Okay, so we got for the layout on this one, we're going to have, in the result, we have 2 square root of 6 plus 12. For the resulting top row, middle row, we have 4 square root of 6. Bottom row, we have 6 square root of 6 plus 12. And all of these will be multiples of what we have for the inside terms for the proposed eigenvector. And guess what? It's going to turn out that this is going to be a scalar multiple. We're going to have the eigenvector is going to be just what we have presented, while the eigenvalue will be 2 times the square root of 6 plus 4. So in this case, A is not, part B is an eigenvector. C, again, we cannot have a 0 eigenvector, and part D, we have to be an eigenvector. Now, in terms of what we have, drawing in the characteristic equation as well as eigenvalues and eigenvectors. And let's say that if we have given the coefficient matrix with 6, -3 as well as -2, 1. Okay, so just setting things up here. Okay, so if I take lambda I minus A, and again, corresponding to a 2 by 2 coefficient matrix, okay, we're going to have a 2 by 2 identity matrix. So you have 1, 0, 0, 1, and taking lambda times I and deducting the elements of A. Okay, so we have lambda minus 6, and then we have 0 minus -3 becomes positive 3, 0 minus -2 becomes positive 2, and then we have lambda minus 1. and looking at the determinant. Okay, so we have lambda minus 6 times lambda minus 1 minus 2 times 3, and just combining the like terms. And we're going to end up with lambda squared minus 7 lambda. And from this resulting determinant, we can say that the characteristic equation, it will be lambda squared minus 7 lambda is equal to 0. Now, for what we have for the determination of the eigenvalues and their corresponding eigenvectors. Okay, so we have by the zero product property from just lambda, we have lambda at 0. From lambda minus 7 setting to 0, we have another eigenvalue set to 7. And just looking at what we have for the 0 eigenvalue. Okay, so looking at lambda I minus a. So again, we have like 0 minus 6, which is negative 6. Then we got 3 once again. We have 2. 0 minus 1 is negative 1. And so for lambda I minus a times the eigenvector x of 1, x of 2. Okay, again, we're going to have for the product, okay, that is going to be equal to 0. And just setting up as an augmented matrix. Okay, so we have negative 6, 3, 0 to negative 1, 0. And just putting in terms of reduced row echelon form, we're going to have 1, negative 1 half, 0. And we have at the bottom, we have zeros. And just looking at what we have in the result, we're going to have that x of 1 is equal to 1 half of x of 2. And x of 2 is a free variable, and we can go ahead and set that equal to t. And so we can say that x of 1 is equal to 1 half of t. So we have for the eigenvector that corresponds, okay, and this can be given in various ways. Okay, and so we can say that we have x is equal to x of 1, x of 2 is equal to 1 half of t and t, and we can factor out t, so you have t times 1 half and 1, and you can just put this as a scalar multiple where we have t at 1 and 2. And I just want to mention, okay, so we can say that we have for a basis. Okay, so we can say that we have for the basis, so you have 1 half 1 or 1, 2. Okay, and this being correspondence to the eigenvalue of 0. Now, for what we have in the case of the second eigenvalue for lambda is equal to 7. And so for what we have in this particular case, right? So for lambda I minus a, so we have for 7i minus a. Okay, what's going to happen here is that in the layout, okay, so you have 7 minus 6 is 1. And then we have 3, 2, 7 minus 1 is 6. And so we have taking what we have for the resulting lambda I minus a quantity times x is equal to 0. And again, so you have with lambda at 7, this is what we have set up. And we have in augmented matrix terms. Okay, so you have 1, 3, 0, 2, 6, 0. And for the reduced row echelon form, would come out to 1, 3, 0 across. And we have zeros in the second row. So we're going to have x of 2 is going to be a free variable. So we have x of 2 is equal to t. And again, from the top row, we had the x of 1 is equal to negative 3 times x of 2. And this will lead up to x of 1 is equal to negative 3t. And so for the resulting eigenvector, okay, so we're going to have x of 1, x of 2, and say we have negative 3t to t. And we can branch out, say we have t times negative 3, 1, or negative t times 3, 1, whereupon t does not equal to 0. And again, we can say that we have for the basis of the eigenvector, you could say we have negative 3, 1, or 3, negative 1. Okay, now for what we have in this problem, letting A be equal to a 3 by 3 array where we have in the top row we have 3, 2, negative 3. The middle row we have negative 3, negative 4, 9. Last row we have negative 1, negative 2, and 5. And looking for the, first of all, for the characteristic equation. Okay, so we have for lambda I minus A. Okay, so we have, again, with lambda I is going to be this time a 3 by 3 array where we have ones running diagonally from the upper left to the right hand corner. And we have in the midst of zeros, okay, so we have like lambda minus 3, 0 minus 2 is negative 2, 0 minus negative 3 is 3, and we have 0 minus negative 3 is positive 3, and we have for lambda minus negative 4, this will translate to lambda plus 4, and we have 0 minus 9, which is negative 9, and for the last row, we have 0 minus negative 1, which would translate to positive 1, 0 minus negative 2 becomes positive 2, and we have lambda minus 5. And again, for the determinant of this difference, okay, so again, just looking at alternating columns, okay, so for the odd number column spaces, we're looking at the positives, and for the even sections, we have negatives. So we have setting up what we have in the determinant. So you had the positive of the quantity of lambda minus 3 times the 2 by 2 array that matches in terms of the minors and the cofactors. So we had the 2 by 2 array with lambda plus 4, negative 9 to lambda minus 5. And then we have minus negative 2. And for the minors and the cofactors, okay, we have in the 2 by 2 array, we have 3, negative 9, 1, lambda minus 5. And then we have plus 3. And you have times, again, we have exposed, you have 3 lambda plus 4, as well as 1 and 2. And looking at attaining what we have in the setup for the characteristic equation. So we have lambda minus 3 times, and we have for the resulting 2 by 2 determinant, we're going to have lambda squared minus lambda minus 2. Then we're going to have plus 2, next 2 by 2 determinant, we end up at 3 lambda minus 6. Then we have plus 3 times the last of the 2 by 2 determinants, which will be the result of 2 minus lambda. And looking at combining like terms together after the distribution, and we're going to end up at lambda cubed minus 4 lambda squared plus 4 lambda. And we have greatest common factor is lambda, and for lambda squared minus 4 lambda plus 4, that is going to be a perfect trinomial. That is going to be a perfect square, and so we have the square of lambda minus 2. So the characteristic equation is going to be lambda times the square of lambda minus 2 is equal to 0. And this will be the backdrop to the eigenvalues. So from lambda equal to 0, we can say our first eigenvalue will be from that factor where we're going to end up with 0. Second eigenvalue will come from setting lambda minus 2 equal to 0, where we have lambda equal to 2. And just the backdrop for the determination of the eigenvectors. So if I work with the lambda at 0, okay, so you have 0 minus 3, 0 plus 4, 0 minus 5, while all the other values remain fixed. So we have this particular 3 by 3 matrix and multiplying by the eigenvector x of 1, x of 2, x of 3, and that product is going to be 0. And just translating what I have in the setup in terms of augmented matrix terms. So we have negative 3, negative 2, 3, 0, 3, 4, negative 9, 0, 1, 2, negative 5, 0, and putting in reduced row echelon form terms. So we have 1, 0, 1, 0. So this will translate out to x of 1 is equal to negative x of 3. Then we have middle row, we have 0, 1, negative 3, 0, and that will be x of 2 is equal to 3, x of 3. And we have zeros running across, so with zeros across, okay, no contradiction, so we have a consistent system. And x of 3 is going to be a free variable, and we can set this equal to t. And from this, we can say that since x of 1 and x of 3 are of opposite sign value, we can say that x of 1 is equal to negative t, while x sub 2 is equal to 3t. So we have for x, the eigenvector, okay, we have x of 1, x of 2, x of 3, and that's going to be equal to negative t, 3t, and t. And factoring out t, we have t times the vector consisting of negative 1, 3, and 1, whereupon we have t is not equal to 0. So this will be your resulting eigenvector. And we say that for the elements, okay, that will make up the basis, which will consist of negative 1, 3, and 1. And again, this will be in correspondence to what we have for the eigenvector value of 0. Now for what we have for the other eigenvalue of 2. Okay, so working with this one, so if I plug in 2 for lambda, okay, so we would have going back like 2 minus 3, 2 plus 4, 2 minus 5, going diagonally. And so we have, for this we have -1, -2, 3, 3, 6, -9, 1, 2, -3, for the result of lambda I minus a, again, as lambda is equal to 2. And so for what we have in this particular case, right, so we had lambda 1 was at 0, and so we just say we have lambda sub 2 is equal to 2. And so for what we have, again, with the eigenvector in general terms at x of 1, x of 2, x of 3, and taking the product between lambda I minus a quantity times the eigenvector equal to 0, I have established, okay, an augmented matrix. Okay, so we have -1, -2, 3, 0, 3, 6, -9, 0, 1, 2, -3, 0, and in reduced row echelon form terms. Okay, so we have x of 1 is equal to -2, x of 2, and what's going to be plus 3, x of 3. And guess what? We have zeros across not only in the last row, but also in the middle row. And this will signal, or these will signal that x of 2 and x of 3 are free. And we'll have x of 3 is equal to t, and x of 2 is equal to s. And so we have, in terms of the variables s and t, so we'll have the x is equal to, okay, the vector where we have -2s plus 3t, followed by s and then t, and then branching out. Okay, so you have s times the vector -2, 1, and 0. And we have plus t times 3, 0, and 1. So those would be our eigenvectors. And again, s and t are non-zero values. And again, the eigenvector basis, we have -2, 1, 0, as well as 3, 0, and 1.